Happy learning! Today we're going to talk about matching problems. Okay, so matching problems often make use of bipartite graphs since whatever's being matched typically can be put into two groups. Okay, so if we're going to pair up clubs and classrooms, right? Those have two distinct types. We'd have the clubs, we have the classrooms, or like employees and tasks. Employees are of one type, tasks are of another. And if we're trying to match them up, a bipartite graph could be useful for that. And so what we're going to look at today is something called matchings, which is basically assigning or pairing up one vertex from the X set with a vertex from the Y set. So given a graph G, okay, so here we just have any graph. We're going to look at bipartite graphs, but a matching is going to be able to be defined on any graph. A matching which we'll denote by M, is a subset of the edges. All right, so it's going to be some collection of edges so that no two edges share an endpoint. Okay, so if we were matching up employees to tasks, it would be like, oh, Jim is washing the floor, and Sue is wiping the tables. Okay, each employee would have one task. They can't have two, and each task would have one employee. They can't have two. Maybe an employee is left without a task, and maybe a task is left without an employee, but nobody's going to be assigned to. Okay, the size of a matching which we denote by just like the absolute value bar. So this is the size of our matching. It's just the number of edges in the matching. All right, so let's take a look at an example. So suppose we have 5 employees and a number of tasks. All right, we want to model the situation with a bipartite graph, and then we'll just find a matching. All right, so here's an example. Here we have employees and tasks. Okay, Dan is our first employee. Dan is qualified to make cookies or bottle syrup. All right, so Dan is qualified to do these two tasks. Jeff can label packages, bottle syrup. Kate can make candy. And make cookies. Lila can label packages. And Tori can label packages and bottle syrup. All right, so here we have 5 employees and some number of tasks. And we want to model this using a bipartite graph. And then we will find a matching. Ideally, we'll be able to match up an employee to a task, so everybody has a task. But maybe there's going to be somebody that's left without a task. We'll have to find out. All right, so let's model this using a bipartite graph. So our X set could be the employees. Our Y set could be the tasks. So here are our 5 employees. Dan, Jeff, Kate, Lila, and Tori. And we have cookies, syrup, package, candy. I think those are our only tasks. So we already know we're not going to be able to assign each person to a task. We just don't have enough tasks. All right, and so let's put an edge between the employee and the task if they're compatible. So Dan can make cookies or bottle syrup. So we're going to have an edge, Dan cookies, Dan syrup. Same thing with Jeff, packages and syrup. Kate can make candy and make cookies. Lila could label the packages. And then Tori can label packages or bottle the syrup. All right, so this here models the table that we were given. But we still want to find a matching. All right, and so we don't really have an algorithm at this point to find the best or biggest possible matching, the maximum matching, if you will. But we can just assign tasks. Okay, so I'm going to label the matching with the black marker. So maybe Dan will do cookies. And maybe Jeff could do syrup. Let's have Kate do the candy, and then Tori can do packages. So Lila, in this case, is left without a task. That's okay. But we know we got as many edges as possible because we were able to assign all of the tasks. Somebody got all, each task has an employee working on it. All right, so no matter how hard we search, we can't do better than this. Okay, so let's look at another example, just a very small example. So suppose we had the following. Here is our bipartite graph. And suppose our matching was this. All right, so if this is our matching, it appears like we can't do any better. If we tried to include any other edge, it would overlap with the edge we already have in our matching. Okay, but it turns out that we made a mistake with our first edge. This was not a very strategic first edge to include because it kind of clogged everything up. We could have instead had this for a matching. And so it's possible on this graph to actually get two edges in our matching, not just one, but from this initial matching, maybe it's not obvious. And so we're going to have an algorithm that helps us go from here to here. And what's going to happen is basically we're going to look for paths. We're going to look for paths in our graph when we have a matching that goes from unhighlighted, so it's going to start unhighlighted, and then highlighted, and then unhighlighted. And then we're going to toggle if it's highlighted or unhighlighted. So we're going to switch this one to highlighted, unhighlighted, highlighted, and we get this. Okay, so that's how the algorithm is going to work. Basically, we're going to search our graph for these alternating paths, and then we're going to toggle them. All right, so let's state that algorithm. Okay, so this is called the Augmenting Path Algorithm. All right, and so what do we need to do the augmenting path algorithm? Our input is a bipartite graph. All right, so we're going to have some x set, we're going to have some y set, and we have our edges. All right, our first step is find a matching. Okay, and we're going to make sure this matching is as big as possible. Basically, if there's any obvious edges we could include one. All right, so if there's any edge where both of the endpoints are not in our matching, add that to our matching. Okay, so I guess that's 2. If there's an edge All right, so if there's an edge where both endpoints are not in our matching, include it in our matching. And then we'll do that until we can't find any more edges. All right, so in this case, right, there's no edge where both of the endpoints are not in our matching. Okay, and so what we're going to do is now we're going to start. So step 3 is if possible. So we're going to look for these. If we could find one, that's great. If we can't, then we're done. If possible, find a path that starts and ends outside of M. Okay, what does that mean? The starting vertex is not highlighted. the ending vertex is not highlighted. That alternates between highlighted and unhighlighted edges. Okay, so we're going to look for paths that start unhighlighted and it alternates between highlighted and unhighlighted edges. Okay, so in our example here, starting at this vertex, our path would be here, here, and here. What we're going to do now is then toggle or switch unhighlighted to highlighted and vice versa. Okay, so if such a path exists, make the unhighlighted highlighted and the highlighted unhighlighted. Okay, so we'll make the unhighlighted edges highlighted and the reverse. Highlighted become unhighlighted. And then we're going to repeat this process until we can't find any of these paths. And once we can't find any of those paths, we know there's a theorem called Burgess' theorem, which I'll state in a second, that says we have the best possible matching. Okay? So let's state that theorem. Okay, so a matching M of a graph G is maximum. So it's the biggest possible if and only if G does not contain the way Burgess' theorem is written, it says does not contain an M augmenting path. But I'll write it just kind of in plain words. Does not contain a path that starts and ends outside of M that alternates between unhighlighted and highlighted. So it does not contain a path that starts outside of M that alternates between unhighlighted and highlighted edges. Okay, so what Burgess' theorem is saying is if we run this algorithm, we're guaranteed to get the biggest possible matching on our bipartite graph. Okay, so let's take a look at an example. Okay, so I'm going to give us a bipartite graph, and then I'll also give the initial matching. All right, so our X set, let's say, has 7 vertices. Our Y set, let's say, is 6. And here is our initial matching. Sorry, this is our initial, this is our just the bipartite graph. Okay, I know it's a little bit messy, but bear with me. All right, so suppose this is like employees and tasks again, and we want to assign tasks to our employees. And suppose our initial matching is this. So this edge, this edge, this edge, and this edge. Okay, so let's see if we can use the augmenting path algorithm to find a bigger matching. Maybe it's impossible, but maybe it's not. Okay, so first thing we want to check, are there any obvious edges we could include into our matching? And the answer is no, right? So we would look at the vertices that are not currently highlighted by our matching and check, do they have any edges out of them that are all, whose other endpoint is not highlighted, and no. So there's no obvious edges we could add. And so now what we're going to try to do is find a path that starts and ends outside of our matching that goes unhighlighted, highlighted, unhighlighted, highlighted, and vice versa. Or not vice versa. And then we'll keep searching for those. And then we'll toggle them, I mean. Okay, so maybe we could try here. Unhighlighted. Highlighted. The endpoint is highlighted, so this path didn't work. I see one. If we start here and we go down, highlighted, and down, both endpoints, you see this? Both endpoints are unhighlighted, and it alternates, unhighlighted, highlighted, unhighlighted. We could toggle this. Let's go ahead and do that. So let me get rid of this. Get rid of the black here. And what happens is we have this becomes black, this becomes black, and our original edge, which I'll just redraw, is back to being blue. Okay, and so now we want to do this again. Keep searching for these paths that alternate between outside the matching, in the matching. Okay, and we could keep searching, but I think we're actually done, right? We do have to check. But let's say if we started here, our only option would be this path, but it doesn't end outside of the matching. If we started here, there's a few that we'd have to check, but we could go down, up, down, up. That does not end outside the matching, so it's not that. If we started going this way, we'd go down. Again, we go this way. Doesn't work. And then finally checking this and up. Again, it doesn't end out. It needs to end outside the matching, which it doesn't. Okay, so this here is the biggest possible matching using on this bipartite graph. Okay, so just to kind of recap how this algorithm works. We have our bipartite graph. We look for unhighlighted vertices and then try to find a path that goes unhighlighted, highlighted, unhighlighted, and then we toggle. Okay, so we go from here to here. That's how the algorithm works. Okay, that's all I have for you today. Let me know in the comments if you have any questions. I know this algorithm is a little bit tricky, so please feel free to ask me any questions in the comments, and I will do my best to answer them. All right, take care. Bye-bye.